So it's a very important chapter on thermodynamic properties. And it's a very long chapter. Before you get all frustrated about how long it is, let me just encourage you to do this. Commit to memory now the list of properties, thermodynamic properties that are important in this class. Start with pressure. Next, temperature. And we're very much interested in not in extensive properties, but intensive properties, specific volume. The next, internal energy, and then later we'll get enthalpy and entropy. But the list is not that long. But sometimes it'll help you in problem solving and this and that, trying to figure out what strategy you need to employ. Make the list of properties, see which ones you know, see which ones you can figure out how to calculate and that are needed to solve the problem at hand. Let's just continue on. So we're going to talk about pure substances. Water, pure substance. Some refrigerant, let's say 12, refrigerant 22, refrigerant 134A. Those are all pure substances. What does it mean by a pure substance? It means if I take the substance and put it in a container, let it sit or whatever I want to do, I come in and I grab a sample out of this location, and a sample out of that location, and a sample out of that location. They all have the same chemical makeup. Let's say the water is a two-phase mixture, and there's some liquid here and some vapor there. In the presence of gravity, liquid will settle to the bottom and the vapor will be over top of it. So we grab a sample. Oh, that one's coming straight out of the vapor. But it's just water. It's the same chemical makeup. Liquid, that's just water. It's the same thing. Hence, it's a pure substance. Same with refrigerants. The ones that get us in a little bit of trouble are things like air. We like to treat things like pure substances. The air in this room, right? If I grab a sample down here versus a sample up there, is it really any different? No. It's a mixture, but the mixture is the same chemical composition. Unless, okay, now you say a bunch of people are back there exhaling, and there's not so much people up here exhaling. But don't worry about the small details. Where do we get into trouble? If you get very cold air. Because what happens to the oxygen and nitrogen that are predominant players in air, it could get to the point where they like to condense and go with liquid oxygen or liquid nitrogen at very, very low temperatures. Then we run into trouble. But high temperatures, things like that, even air we'll treat as a pure substance. First clicker question. Air consists of a mixture primarily of diatomic oxygen and diatomic nitrogen at 25 degrees C and 1 atm. Can it be treated as a pure substance? Is everybody in, or you need more time? All right. Well, I don't know what 16 people are thinking, but 60 people are thinking, yes, it can be treated as a pure substance. All right. How would I make it so that yes is not the correct answer? Well, first of all, you look at the temperature and pressure. It's pretty warm, reasonable pressure. If I drop that temperature, drop it, cryogenic temperatures, all bets are off. Don't treat it like a pure substance, okay? Yes?
About what temperature does it start?
I don't remember the boiling point, but if you leave it at 1 atm, then the boiling point may be, 70-something Kelvin for nitrogen? And I don't remember what it is for oxygen, but it's cold. It's really cold. Oh yeah, it'd still be fine. Even at negative 40 degrees Celsius, it'd still be fine. Any other comments? Now you start playing with the pressure, and you can make that change a little bit too. But all right. We talked about phases, solid, liquid, vapor. What's the real distinction on a molecular level? Whether or not the molecules are have some sort of force in between them. When you have a vapor, the molecules exist primarily with no force in between them until they hit and they strike each other, and then they recoil and they go on their merry way. But most of the time, the molecules are as if they're all by themselves, especially in an ideal gas. But when you have a liquid, there's pretty significant intermolecular forces that hold the molecules together in a liquid phase. And a solid, even stronger, even stronger. And you have to pump energy in, raise the temperature to melt, to go from solid to liquid, and then the boil to go from liquid to vapor. And what you're doing is you're breaking up those intermolecular forces, overcoming them, adding enough molecular energy to overcome them. So we have going from solid to liquid, melting. What's the opposite? Liquid to solid, freezing. What's the liquid to vapor? Boiling or vaporization, evaporation, something like that. A couple different words that mean things. But vapor to liquid, condensation. It's condensing. The harder ones would be solid to vapor. Sublimation. Where do you see that in your real life? Sublimation. Solid, dry ice where they put CO2 and that's used. You can still buy it and use it to keep things cold for a long time, especially if you need to ship it somewhere and you don't want the liquid. If you use water, frozen ice, then you get liquid, and that can be a nasty thing. But you put dry ice in, it's cold, and there's no liquid. At least not from the CO2. There's another application that we see. Anybody ever get ice cubes out of a tray in a refrigerator? Yeah, you crack the tray and knock out the ice cubes. You ever looked at the ice cubes that have been in the tray and nobody's cracked it for a couple months? And you look in there and it's like, hey, erosion around the edge. Anybody seen that? Yeah. Basically, the solid water went straight into vapor. So you can see that in your refrigerator. Take a look at some. I know our ice trays don't last long, but if you left one in for a couple months, you'd see the evidence of that. Now, the vapor to a solid, well, some sort of deposition. All right. Is it possible to have a mixture of some liquid and some vapor in thermal and mechanical equilibrium in a system? You say, yes, it's possible. Answer, true. Say, no, I don't think it's possible. Answer, false. It is possible to have a mixture of some liquid, some vapor in thermal and mechanical equilibrium in a system. It is true. You can have that. They can be. So what I can do is I have a container conceptually, and I fill it with H2O, water. But it's at a certain temperature and pressure where some of it will be in the liquid state. I know that we spend a lot of time on Earth's surface, right? So the gravity would affect the presence and draw that liquid. It would settle at the bottom of the tank, and above it would be the vapor, all right? And so in that case, sure, that's what we'd have. We would have, if you stuck a thermometer in here and a thermometer in there, same temperature. Stick a pressure gauge right there and a pressure gauge right there, same pressure. Only thing I'm going to have to deal with is a little bit of hydrostatic pressure in that liquid. But that's a reasonable assumption that we just don't have a pile of liquid such that I'm talking about the pressure at the top of the liquid surface different than the pressure at the bottom of the liquid surface. I'm just talking about the pressure of the liquid, neglect the hydrostatic if I have a little layer of liquid in there. So that's what we mean by thermal and mechanical equilibrium. Yes, you can have water. Now, what would happen if I moved this to outer space? So now I'm going between planets and there's 0 G. Is the liquid going to settle to the bottom? Nope. And then if you shake it up a little bit, it'll all be dispersed out. Now the liquid will try and coalesce because of those intermolecular forces. But you probably have something like a cloud. All right, something like that. Because the liquid, you could sometimes see that, right? it's a different, to say, yeah, that's the liquid and that's the vapor. I can see a difference in the visual property. State principle. Did we talk about this already? For a simple compressible system, that's the things that we're interested in, two independent intensive properties fix the state such that other intensive properties can be found. What's our list of properties? Pressure, temperature, specific volume, internal energy is big enough list. I have 4 of them. Let's say I'm interested in calculating one of the 4. I don't know it. I need to calculate it. If somehow you can strategize to get the values of the some other 2 of the list, in principle, you can get the other 2, right? So it fixes the state. So it'd be like this saying, I really want to know the pressure. If somehow I could deduce the temperature, or maybe it was given to me, and the specific volume, figure it out, calculate it, or maybe it was given to me, then in principle, I can go and theoretically get the pressure, because 2 independent intensive properties, fix the state, allow me to get the other, not independent, but other properties. They're not independent then. They're dependent on the other 2 properties. Here's another one. Internal energy, I could theoretically get it if I knew the temperature and specific volume. What's common is, give me these 2, I'll give you these 2. But in principle, you could mix it up. Okay? Usually it's give me temperature and pressure, make sure they're independent, and I'll give you specific volume, as well as I'll give you internal energy. Now we talk about representing property data for a substance and it's in equilibrium on a plot. Well, start with the 3-dimensional plot. A 3-dimensional plot where you have 3 axes. The axes are temperature, specific volume, and pressure. Can you find the axes on this plot? All right. Temperatures along this way. Where's low temperature? Where's high temperature? Is high to the right? Is this high? Yeah. They didn't label it, did they? They didn't put in arrows. They didn't say it starts at 0. But they just said this is temperature, right? Conceptually, this is a plot of some data. But let's get the axes. So you could start at 0 Kelvin, although that's kind of unrealistic. They don't really put it there. But you can't put it, there's nothing to plot going below 0 Kelvin, is there? Or below negative 273 C, is there? There's an absolute 0. Next axis, the specific volume, V. What were the units on specific volume? Meters cubed per kilogram. And when I talk to myself about specific volume, I use 2 hands. And I take them and I visualize my 2 hands encompassing a volume. All right? And then I think inside that volume, I have a kilogram of mass. Now, if this kilogram of mass needs to occupy a larger volume, what did specific volume do? Increase or decrease? Kilogram didn't change. What did the specific volume do? It increased. That's so what we have is this is getting larger volume for the same amount of mass. Larger specific volume. Can I have anything, what would be a minimum specific volume? A reasonable minimum value for, could I have negative 100 meters cubed per kilogram? How about 0? That makes sense? That would be a minimum, 0, and then it goes up. Okay? So you could think, okay, then it's going to go up. How about pressure? Does it have a minimum or can it go to negative whatever pressure? No, it's absolute 0 pressure is kind of a minimum. We could measure things from atmospheric pressure or total pressure. A lot of our thermodynamic properties and the tables in the book, if that's a pressure there, it's absolute pressure. It's absolute pressure, okay? A lot of times we talk about gauge pressure when we talk about the pressure in that tank, or we talk about the pressure in the tire of my automobile. All right, so this is a direction of increasing pressure, and you could think about 0 and 0 being there. So we have the 3 axes. Now, thermodynamic property says Two independent properties give me the other. Think about fixing a temperature. Oh, I'll just pick this one right here. Fixing a specific volume right there. And there's only one pressure. And that's plotted as a point right there. That pressure is a height above the, in the third dimension, a height. So if somebody says, what's the pressure if it's up here at the same temperature, same volume? It's not on the surface, it's above. That's not in thermal equilibrium, not in mechanical equilibrium. It's not a state of equilibrium. Okay? There's only one and only one pressure from the state principle at which, for that temperature and that volume, it's in equilibrium. So don't think of this as something other than like a sheet. It's just a plot. Above it is air, not meaningless points, and below it is air. It's meaningless points. It's just a surface. True? All right. Now that we have the axes and the concept of plots, press forward. Can you find on this surface, PVT surface, single phase regions where you would say, oh, in that region it's all a vapor? Where would that be? All where it says vapor. It's not too tricky, is it? All in here. True? Where would it all be a liquid? Where it says liquid. That's too dark of a color, I think, but you see what I'm talking about. And then where would it all be a solid? Right in there. Now, let's talk a little bit about the steepness of the surface. Which surface seems steep in this 3D rendition? The solid seems very, very steep, meaning that if I have a specific volume right here and then I try to compress it, right? Make it go to a smaller volume, what's the pressure going to do? It's going to scoot on up. Liquids and solids are essentially incompressible, and you can see that. Same out here in the liquid. If I have the liquid specific volume and then I try to reduce it by compressing it, the pressure goes up. Liquids are essentially incompressible. Solids are essentially incompressible. We approximate them to be incompressible. Are they truly incompressible? No. They will change volume a little bit as you boost the pressure. Liquids a little more than solids. What about the not so steep portion? That would be the vapor. Right? So those are the single phase regions. Where exactly is this single phase region for the solid? Well, if I trace the boundary, it's kind of like there's an edge over to this edge, up to this edge, down. Does it somehow wrap around on this top surface over here, that solid region? No, it doesn't. This always is tricky now. Well, if pressure can continue to go up, what did they do right here? They stopped plotting it. They took and cut it off and said, I can't continue to plot, so I'm going to stop plotting it. So what is the meaning of all of this space up here? It's just where the surface, it got truncated. It's not a kink and the surface now goes flat with respect. Okay? How about this wedge-shaped region right in here? That's where they truncated with respect to specific volume. Okay? We know we can keep going, but let's stop it somewhere and focus our attention. Then what about the backside? You can't see it, but they had to truncate it there. They had to cut it there. They stopped it at some temperature. But the temperature can keep going and going and going. Physicists like to take things up to extreme temperatures. And then what about this shaded surface right here? It's just not any meaningful data points. It's not part of that surface. It's just where the plot, there's no point. It's a cut, okay? So you do have regions that can fool a student when they first look at it. Then you ask yourself, why did they color code this little area right there? I don't know. Why did they not color that area right there if they colored the other area? I don't know. If I was, the technical editor, I'd probably say either color all the cut areas on your 3D rendition or don't color any of them, because they colored this one and they colored that one, but they did not color that one. See? All right. Why did they draw these lines going through? Well, to try to help visualize a line of constant temperature. This is all a line of constant temperature, but it's not physical right here. It's just trying to help get it back. Similarly, it's not physical right there. It's where the pressure is dropping dramatically down to zero pressure. All right. So there's a nice demarcation for the solid region, isn't there? It's kind of like that. What about the demarcation for the liquid? It kind of goes cutting along here. It then goes along this shape up to a point called the critical point. But where is the separation? If I said, here's a substance at that point right there. Is it a liquid? Is it a vapor? Or is it a solid right there at this point on the surface? Well, you'd say, I wish you would have asked me the question about this point. Then I'm really confident that's a liquid. But this one is a little toss-up. Is it liquid or is it vapor? Move the point a little bit over here. Is it liquid or vapor? Hey, put the point down here. It's clearly vapor. Right? See what we're doing? We're moving that point around. So there's nice lines of demarcation to separate, say, hey, this is a line that tells you it's all vapor out in this region. But what about a line, a nice clear line right there? There isn't one. It's supercritical, and we'll talk about it some more. Right? Makes sense? Oh, another clicker question. There is not a clearly distinguishable line between the solid and vapor phases at low temperatures, liquid and vapor phases at intermediate temperatures, or liquid and vapor phases at high temperatures. Do we have enough time or you need more? Well, what is it? It's this region in here is what we're just talking about, where it lacks a clear distinction between not the solid and the vapor, it's the liquid and the vapor. So the A, B, and C are the contenders. A goes out because there's not a problem with the solid. But I look at it and I say, is that at high temperatures or low temperatures? It's high temperatures. Best answer is so now we want to talk about two-phase regions. We got our single-phase regions down, but what about two phases where you can have liquid and vapor coexisting in thermal and mechanical equilibrium on this surface? What does it look like? Well, this line right in here from the critical point going down is what we call saturated vapor states. Meaning, if I try to cool it a little more, it's going to go, depending on how you're cooling it, if you're trying to cool it at constant pressure, it's going to go into and start to condense. So it's on the cusp. I have vapor, oh yeah, it's vapor, but if I try and cool it a little more at constant pressure, it goes into liquid and I get some condensation. Over here is saturated liquid, meaning that I'm in the liquid state. Maybe think about right here. I'm at constant pressure. I warm it up a little bit. I come up here. It's saturated liquid. If I warm it up some more, I not change the pressure. What I'll get is I'll get some vapor forming. Okay, so this right in here is a two-phase dome where I have liquid and vapor mixture all in here. Okay, where do I have another two-phase dome zone where I have liquid and solid coexisting? Yeah, can you see that? It's right in here, true? And so one of these edges is going to be called saturated solid, and one of these edges is going to be saturated liquid. And maybe I put a really high pressure line at constant pressure, and the solid will come around like this, then it'll cut through there, then it'll wrap around like that. And so you could see that if I have a solid and it's really cold and I heat it up at constant pressure, it's going to get up until it becomes saturated solid. Then if I heat it up some more, some of it's going to go liquid. And as it goes to liquid, what's the volume going to do? The specific volume. Take my two hands. Going to expand. As it turns from solid into liquid at constant pressure by trying to dump more heat in and trying to increase the temperature. And then it becomes saturated liquid. As I dump more heat in, the temperature will go this way, and the temperature will actually go up. I'll get warmer liquid. So there's the solid vapor two-phase region, the liquid vapor two-phase region. I'm sorry, the solid liquid. Where's the solid vapor two-phase region? Yeah, in the bottom. And could we kind of shade it in and really take a look at where it's at? It would be all of this. No, that doesn't help me, does it? Let me try this color. All of this region in here. All right? So what is this zone right in here? It's saturated solid where it's going to become vapor. And this line right here, it's saturated vapor where if I try to cool it, it's going to become solid. And in here is a whole bunch of two-phase mixtures. All right, so those are lines where I have saturated solid, saturated liquid, saturated vapor state. Why do they call it saturated? Because you nudge it a little bit and something happens. It starts to change phase. All right, are there any, well, we already talked about this dome. Why do they call it a dome? Because it's shaped like a dome, and we do a lot of engineering applications deal with water or other substances like refrigerants that are changing phase between the liquid and the vapor phase, either boiling it, evaporating it, or condensing it. Okay, we have a lot, refrigeration as well as power cycles. So we spend a lot of time in this dome. What's at the top of the dome? Critical point. And that's that last point where, you know, once I'm above the critical point, there's not a clear demarcation between what's a liquid and a vapor. It's actually called supercritical fluid. Supercritical fluid. Okay? And then the other point or line of interest is a triple line. Why do they call it a triple line? Because three phases can coexist in equilibrium, all at the same what? Condition? Are you joking me? No. Here it is. Guess where it is? It goes from this point out to there. And that's a line. So that's a triple line. Okay? So we could have it starting to produce some vapor going that way, some liquid, think about going that way, as well as some solid, all coexisting. Now, that line is at one unique pressure and at one unique temperature. It's the triple point value, temperature and pressure. Just like the critical point has one unique pressure and one unique temperature, often put TC for the critical and PC for the critical value. We're going to, let me ask this clicker question, last one for today. Is it possible to have a pure substance being 1/3 liquid, 1/3 vapor, 1/3 solid, all in equilibrium? Yes or no? And it would all be at that triple line condition. Okay? Answer A. All right. All right. So the next time we'll pick up and talk about different surfaces, what they look like. There's a difference between these two surfaces. I'll pick that up next time. But now let me hand back the exams.